Now let's turn to boosting. So the idea behind boosting is always that the new models have to correct the remaining mistakes of the ensemble. So imagine that you have a first model, G1, and this model makes some mistakes. The idea is then that we train a new model, G2, which has to correct the remaining mistakes of G1. Now we do that by forcing G2 here to correct the mistakes of G1, and we can do that by reweighting the training data. So if G1 misclassifies some instances, or in regression doesn't get close to the true value, we increase the weights of these instances, which means that G2 now has to correct these harder instances correctly. Now, these models, G1, G2, they should be simple. They should be high bias, low variance. First of all, because we want them to be different, and we want them to each focus on certain subsets of the data, and underfitting models are ideal for that. It also makes sure that if we reweight the data, the new models will be quite different than before. And each of these will be an expert on some parts of the data. So basically, we will build an ensemble of experts, each being an expert on some part of the data, and the sum of all the predictions of these experts should give us the correct answer. So that's why we call this an additive model. The final predictions, like F here, are the sum of all the predictions of the different expert models. Okay, now these will be weighted WI, and this weight is very important. This weight tells us how good the model did. And so every model gets its own weight WI. And we want to first train these models G, and we will evaluate how good they are using an instance-weighted error function epsilon. Right? So it's instance-weighted. So depending on the current weights of the instances, we will evaluate how good this model is doing. Right? So it's really pushed towards building a model that makes good predictions according to these weights. Now, the loss function that you want to optimize is exponential loss. So it looks like this. It's basically the exponent of this guy. And this guy is the instance-weighted error of the total ensemble F. Right? So basically we evaluate how good the model is doing according to the current instant weights. Now, how do we get this weight WI, the model weight? And we can do that by taking the differentiable of this loss function with respect to this WI. And if you derive that, you will find that the weights takes this form. So it's basically the logit function of the error epsilon. Right? That's a theory. Now let's see how this looks like in real life. So one of the simplest algorithms for doing this is AdaBoost, or adaptive boosting. So first we start with setting all the weights of all the samples to 1 over n being the total number of points. So they start with all equal weights. Then we build a first model, and in AdaBoost, these are always decision stumps. Right? So they're really like trees with only one split. Then we compute the weight WI, and this is the function for that. Now, what does this actually mean? We recognize this guy. This is the logit function, right? So if the error rate is some value between minus infinity and plus infinity, this guy basically plots it in some value between 0 and 1. So if the error is large, the weight should be small, and vice versa, so it will look like this. Right? This is the W, and this is epsilon. Right? So it basically just maps the error to a value between 0 and 1. And then we also add a learning rate. This learning rate makes sure that we don't converge too fast, right? So remember, F is the sum of the weighted models, right? Something like this. Now, if you would directly learn these weights so as to minimizing the error here, this would converge very fast. And this can be detrimental, as we've seen in gradient boosting, for instance, in a gradient descent. If you take too large steps, you may overshoot, or you may go up and down and oscillate basically between two values. And similar thing happens here, right? So say that all your points have a weight. It could be that adding a model increases some weights by a lot, and then a model gets those right but gets others wrong, so then all these guys get a lower weight but other points get a larger weight, and then after you correct for this, then these get low weight and the other guys get a high weight again. So you can sort of not smoothly find a final set of weights and a good solution. So to make sure that you don't have this oscillation so much, we add this learning rate, lambda, also called a shrinkage. It basically makes sure that this model smoothly converges to a good solution. This is an important hyperparameter. So setting this correctly can definitely speed up or improve the solution that you find. Now, be a bit careful because, making alpha smaller will result in a smoother convergence to a good solution, but it will also require more iterations. So you have to build a larger ensemble to get there, to reach convergence. Okay, now, so we have our first model, G1. Now we want to build, and we have computed the weight, W1. So now we have our first predictions, F. Now we want to build the second model, G2, to correct the remaining mistakes. And we do that by increasing the weights of all the incorrectly predicted examples. So the new weight, as I plus 1, is the old weight times the exponent of the weight of the previous model. So the current model, yeah. So what this means is that if you have a good model, so Wi is large, and it still incorrectly predicts some points, then these points are obviously very hard, and we need to increase their weight by a lot. Right? So if Wi is large, this update will also be large, and we will increase the weight by a lot. If the model is not so good, this will be smaller, and we will only see a small update in the weights. If the model is correctly predicted, so if the point is correctly predicted, then we can decrease the weight of that point again, according to, again, how good that model was. Then we normalize the weights, so they add up to 1, and we repeat. Right? So we built the first model, G, we've computed the weight, W1. We have new weights for all the data points. With these weights, we train a new decision stump, G2, and we compute the weight again, and we progress in that fashion up until either we reach I iterations, or we observe that the error converges and we can stop. Now, AdaBoost has a number of different variants. The simplest form is just discrete error boost, where the error rate is simply just 1 minus the accuracy. That works well, but remember that decision trees can also give you probabilities, right? So we can use those. So real AdaBoost uses the predicted class probabilities of the trees. And this typically gives you a smoother convergence, typically works better. If you want to do regression, that's also possible. In that case, again, you have different choices for this error function epsilon. Most often used is just the squared error. So if you make a prediction y hat I sub I, we just compute the difference squared at every point. That's the total loss of a model. Instead of squared, you can also go for the linear loss, just the absolute value, or exponential loss if you want to. Gentle boost is another variation. This is very close to real AdaBoost. The only thing that changes is that we add a cap on the weights of the models. So we don't allow that one model gets a very large weight. We put basically a maximum on it. So this one very good model will still count a lot, but not too much, so that other models can take over from it. And finally, LightGBoost. So remember that AdaBoost corrected the exponential loss here, which led us to this function for the weights of the model. Well, LightGBoost replaces that with the logistic loss, which you remember from a logistic regression, for instance. And this will give us a different function for computing the weights of every model. It's quite a bit, it looks quite a bit more complicated. That's basically the main thing that changes. And it's also a very good, well-performing version of boosting. Now let's see how this looks like in action. So we have some points. Let's reset to 0. So in the beginning, all the points have equal weights. So all the points have equal weights. And then we build our first model. This is the decision tree, decision stump, right? So there's a 1 split. And so all the points with the red background operated red, and with the blue background operated blue. So now we see that these are indeed all red, but there are a few points here which are blue. So these are misclassified, which means we are going to increase their weights, right? So the red dots here will have a smaller weight now, and these 5, 6 blue points here will get a larger weight. And in this figure, the size of the dots represents the weights, right? So if the dots get larger, the weights increase. Okay, on the other side, all these blue guys are rated correctly, so they remain, or they get a smaller weight, while all these red points here, which are a lot, they're all misclassified, so they will get a larger weight. Okay, now the next decision stump will have to correct for this. It will have to focus on the large dots here. Let's see what that does. So we add iteration 2. Okay, so now because all of these red points have high weights, this resulted in a model which basically always predicted red. Right? Okay, that's possible. So we take this. So that means that all the red points will decrease in value, all the blue points will increase in value. Then we go to the next model. Okay, this predicts this. So here again, we have a couple of blue points here which are misclassified, so their weights go up. And you can already see like these were smaller and these get larger. And let's skip ahead a few iterations. So you will see certain points will get bigger over time because they're very hard to correctly classify with decision stumps, especially the ones around the circle here at the intersection here. They're much harder to predict, so they will get larger weights. While the points in the center or at the outskirts here, they're easier to predict, so they will get lower weights. So you can already start seeing this. And if you go towards the end, you will see that it will keep building all these stumps, trying to correct the mistakes of the previous models. And you'll see some points emerge as being very hard to predict and other ones very easy. So that's in a nutshell AdaBoost. Some examples in real life. Well, this is toy data, of course. So here we have these two banana shapes. We see one tree does that, 3 trees gets a bit better, and 100 trees gets up to 95% accuracy, so it's pretty good. And you can see how the combination of all these trees gives you, again, this blocky shape that we also saw in random forest, but uses a different way to get there, of course. Here we have this donut shape. Again, we see it learns a blocky kind of shape here, which as closely as possible represents these points. And these two blobs here, again, it finds a pretty good model, 95% accuracy. But still having this blocky nature, of course, you can't really get around that. Okay. If you look at the bias variance analysis, we see, well, we said that boosting reduces bias, and this is exactly what we see here, right? So on the left here, we have the situation where we had boosting with just 1 tree or 2 trees. So in this case, because we use decision stumps, there will be high bias error still. And if we go up to maybe 1,000 or more decision stumps in our boosting ensemble, we can see that the bias drastically drops. Right? So that's exactly what boosting does. By correcting the mistakes of the previous model, the ensemble reduces bias directly. You can see some improvement in variance as well. This is quite typical. But that's not the main thing that it does. So you really want to start with models which have high bias and low variance, because this method will mainly reduce the bias. So the improvement in the error is mainly due to the reduction in bias error. Now you can take this too far. If you, like the opposite of what happens in the random forest, if you add too much tree to your forest, you will get some more bias error. In this case, if you add too much trees in your boosting ensemble, you will get a bit more variance, right? Because, yeah, the weights of the points get larger, so the models will be forced to make increasingly unusual predictions, and this will generate some variance errors. There's still a trade-off here, but typically, the more trees you can build, the more you can drive down the bias. The second thing you can do is gradient boosting. So remember that in boosting, every model aims to correct the mistakes of the previous models together. And in gradient boosting, this happens directly, right? We build a first model, say G1, and this model will make some mistakes. And we call those mistakes the residuals, or actually we call them the pseudo-residuals. Now, the pseudo here just means that it's a temporary residual. It's not the residual that we saw in linear models, for instance. It's like the current temporary error that the ensemble makes, right? The pseudo residual. So we built the first model, G1. We compute these residual errors. And then the next model directly predicts those, so that the sum of the two gives you exactly what you want F, right? So in principle, this model would stop after 1 iteration. We don't want that, so I'll get back to that. But it's just so that you can see this. So if you have a first model G1, it will make some mistakes, and the next model exactly wants to predict those mistakes, right? So if G2 is flexible enough, it can do that in one go, and you're done, right? Now, first of all, we're still doing boosting, right? So we want our models to be simple. Now, in gradient boosting, the models are a bit more complicated, so we typically allow decision trees up to a depth of 2 to 5, because they should be complex enough to actually learn the residual errors, but not so flexible that it does directly, that you're done in one go, one iteration. Now, a second way to avoid that we converge so fast is to add a learning rate of shrinkage. So here we use the exact same symbol that we used before for gradient descent, nu, or eta, sorry, eta. Right? So we add a learning rate to this. And this learning rate, again, attenuates each model's contribution. And it allows us to control how fast this will converge to zero error. Now, if you look, this is again an additive model, right? So it's this formula. F is the sum of an initial model, G is 0, time plus some learning rate, and every other model. We could write this also like this. So the current model Fi is a previous model Fi plus a learning rate plus a new model Gi, built this iteration. You may recognize this from gradient descent, right? Remember that the new weights I plus 1 were the previous weights plus eta times the gradient, remember, of the loss function according to the weights. Now in this case we don't do gradient descent over the weights, we do gradient descent over the predictions f, right? So that means that this gives us a way to calculate these residuals, to find a way to calculate the residuals. Okay, so now if we want to do gradient descent, this function Gi has to predict the residuals, and these residuals should be the partial derivative of the loss function according to the predictions of f. Right? So that's what we will use to find a formula for computing these residuals. That's the high idea. So basically what we're doing exactly gradient descent over the predictions of our model, right? And every time we add a new component, a new model to our ensemble, which will take a small step towards giving you better predictions. This is exactly what gradient descent does. Okay, now this guy looks scary, but in practice you will see that this will become very simple to do. Now let's see how we do gradient boosting. First for regression. Okay, now in regression, the loss function that you want to use is square loss, which you've seen before. We add this thing here in front. You will see why in a minute. Now the pseudo-residuals, again, are computed as the gradient, right? So it's the partial derivative of the loss according to the predictions y hat here. If you do that, take the so y hat is this guy. So it means we get the 2 to the front, so minus 2 times this guy, plus, because this is a minus here, we get plus minus 1. Okay, now you see that this cancels out, and this cancels out, and so you're stuck with this. That's all there is to do. So the residuals under this loss function are simply the prediction error for every sample. Right? So if you have to predict a value 5 and you predict 4.5, your residual will be 0.5. Okay, it's as simple as that. That's sweet, right? Okay, so knowing this, let's start. So we build an initial model G1. Now in regression, this is the simplest model possible. We just predict the mean of all the values, of all the target values y. Okay, now for the next step, we are first going to compute all the pseudo-residuals. Basically just for every point. So if you have some points, and this is the mean, the next points are going to be the residuals, the difference between that point and the mean. Then we fit a new regression model to predict exactly these residuals. Okay, and then we update the predictions. So we take our first mean prediction plus the new prediction for the residuals times the learning rate eta, and we keep doing that until we converge. So either we converge when we reach a preset number of iterations, or when we do early stopping. In this case, we just observe, we use a validation set to observe whether performance still improves or not. So if this is a validation error or tested error, typically you take a small part of your training data for validating that, and this is the number of iterations. You will look at this curve, and if it doesn't improve for a number of iterations, you just stop. Okay. It's similar to, it's exactly what you do in gradient descent. Okay, let's see this in action. So, okay, so on the right here, I have some data points, and I basically want to learn a regression function that will go to these points. Okay, now we're doing boosting, so we start with a simple model, which is this red one. It's a simple two-level decision tree, which gives us this stepwise function, as we saw before with regression trees, right? Now we compute the residuals for every point. So here we get a large residual, so this will, and if you plot that here, this will be large, so this is this point here. So all these guys have large residuals, large negative residuals, so they end up here. These ones are around 0, so they end up here. This is the 0 line. These ones have a large positive residual, so they end up here. Okay, so this is the plot of all the residuals for every point. Now our next model will exactly predict these residuals. Again, because this is a simple decision tree, we will get the stepwise function, so we get this red curve. Okay, next step, we're going to add this curve times the learning rate to this red curve, and we'll get this model, which is already a closer stepwise function. It's already closer. You can see the residuals get smaller. So you've seen between step 0, where the residuals are large. In step 1, the residuals are already a bit smaller. In step 2, they're even smaller. And if you keep doing this, you'll see over time, first of all, the residuals all get smaller. They get down to 0 or close to 0. And on the right, we see that this regression function now very closely matches our data. Right, so this is a very clear visualization of how boosting gradually, by self-correcting the previous mistakes, finds a complex function, basically, that can learn any complex concept that you wanted to learn. Now, you can take this too far. If you, because this is quite simple data. If I would take it too far, you will see some overfitting happening, where it like tries to correct for one specific residual and so on. So if you take this too far, you will see some overfitting happening, but overall, it's still not too bad for it. Yeah, you can see it never really goes. It doesn't overfit nearly as much as a normal decision tree would do. But you can see it definitely reduces bias, right? So compared to this very biased model in the beginning, the new model is much less biased. Basically, we reduce the bias with every iteration that we do, and the model gets more complex. Now let's see how this works for classification. And this will be reminiscent of logistic regression, right? So we will again be solving classification problem through regression. So our base models will again be regression trees, and each regression tree has to predict the probability of a positive class P. Now, if you have a multi-class problem, like a 10-class problem, you will have to train one tree per class every iteration. The log loss is used as a loss function, same as in logistic regression. And remember, the log loss looks like this. So intuitively, the probability of the positive class will be a value between 0 and 1. And the loss, so say that the true label is 1, and we predict a probability of 1, then the loss will be 0, and it will gradually, exponentially increase up to infinity if you click goes to 0, right? Something like that. So if you correctly predict near 1, you get a very small loss here. If the class is 1, you predict something like 0.1, then you'll get a very large loss component. Okay, so the pseudo-residuals are again defined as the derivative of this loss with respect to the predictions, which will in this case translate to the derivative of the loss with respect to the log of pi. And if you compute that, this is again not so obvious, but well, the first term is easy. This will just be the derivative of this guy according to log pi is just I sub I. And this term will derive into pi. So the residual Ri is the difference between the true class and the predicted probability. Right? So if you have the true class 1 and you predict 0.9, then your residual will be 0.1. If, on the other hand, you predict wrongly, say you predict that only 0.4 probability of being positive, then of course you will get a large residual. Okay, and if your class is 0, then it's the opposite, right? And you predict 0.9, you will get a large negative residual to correct for. Okay, so that's how we compute residuals. And now let's do the algorithm. So we start with initial model G. 0, and basically all the information it has is just the ratio of the number of positives over the number of negatives. So it predicts just a log over the odds. That's it. It's a starting point. The first iteration, we first have to compute all the pseudo-residuals as we defined here. And then we build a regression tree to predict exactly these residuals. Now, how does that work? So remember that we are dealing with trees here. So say we have a leaf here, and we have 2 points. Say that this is positive, and this is negative, and this has a residual of 0.2, and this has a residual of minus 0.1, for instance, right? So first of all, so the prediction of this leaf is defined like this. And this will basically mean that for this example, it will be 0.2 minus 0.1 divided by, so there's one positive, one negative, so that will be 1 over 2 times 1/2 for the positive class plus 1/2 times 1/2 for. So this is this one. Okay, that's what this is. So yeah, this will be 0.1 divided by 1/2. So 0.2, right? That's a prediction of this leaf, right? So yeah, we have one positive with some residual and a negative with a small residual. So the predicted residual will be 0.2. Hopefully. Right. So after we have computed that, we update the ensemble predictions. So we take all the predictions, we weigh them by a learning rate, and we keep doing that. And so we keep doing this iteration until either we reach m iterations and we stop, or we can also observe the loss versus a validation set. So we take a small part of our training set aside and we use that as kind of a validation error, validation loss, and this should be the number of iterations, m. And say that this goes down, but then it doesn't go down for a number of times, then we just stop at that point because we don't expect it to improve anymore. Okay, that's it for classification. Let's see how this works in practice. So again, our initial model, it's a two-level model in this case, in this example. So the first tree predicts this. Then the next iteration will have to predict the residuals again. So the next model is a bit better. So we end up with this. So yeah, in this case, in this visualization, we show the predictions for the entire ensemble, right? So we build two trees, one splits like this, one splits like this, and the sum of that will be this prediction here, which is already quite good. And the size of the dots here is the residual weight. So if we increase that, you should see that again, points which are hard to predict will get a larger residual every iteration. So these residuals, they get updated every iteration, right? And every model tries to predict these correctly. And you can see it makes some forays into that area. And you can see that over time, this model, this ensemble will make better and better predictions with almost zero residuals for most of the points and only some points having some significant residual left. Right. Some other examples, again, are banana shapes. You can see that gradient boosting, yeah, it does a bit more effort. So you can see the blocks are smaller. And yeah, it does reach a good performance. Again, here, it's still blocky. That's just what it is. And here, these two blobs here also, it tries to find a good solution for that as well. So building many trees definitely improves performance. Like in this case, performance goes from 65% accuracy for one tree to 78 for 3 trees and 80 for 100 trees. If you do the bias variance analysis, again, this is the number of trees in our gradient boosting ensemble. So for 1 or 2 trees, we see we have high bias, but we see that even with a few iterations, gradient boosting reduces bias by a lot. So it typically reduces bias much faster than AdaBoosting does. And it's still tends to improve over time the bias situation. Variance remains low as expected. But again, if you would take this too far, you will see variance go up again, especially because it's trying to like predict these weird points, and this will create some variance over time if you take it too far. Again, we can also use gradient boosting for feature importances. Again, this will be based on many trees, but because the trees are still quite shallow, they only have like 4 or 5 layers deep, you will still have a lot of features which will have 0 importance because they never occur in any of the trees. It's useful whenever you know that many features will not be important, then this will give you exactly 0 prediction, while random forest will give you at least some feature importance. But overall, these ones are used less, so most people would go to the feature importances of random forests. Okay, so gradient boosting is definitely among the most powerful and widely used models. So there, if you have any machine learning competitions, very, very often these are won by gradient boosting approaches. They work well on, again, on heterogeneous features, different scales. You don't need to invest too much in preprocessing, although I'll come back to that in a minute. So they're very flexible to use. They typically perform better than random forests, but they do require a lot more tuning. And this is where, in challenges, where it comes down to. Typically, you win these challenges by very carefully tuning your gradient boosting approach, also by training longer. Well, you don't just train for 100 or 500 iterations, you train for 10,000 or 20,000 iterations. And just like Zen trees, it doesn't extrapolate, it doesn't work well on high-dimensional sparse data because there's no good way to split this data. It has a number of hyperparameters that we need to train. First, the number of estimators, the number of trees in your boosting ensemble. Higher is better. You want a lot of these, but if you take it too far, it will start to overfit. So you want to counter this overfitting in different ways. The obvious way of doing that is to play with the max depth of the trees. So if you see overfitting, you may want to reduce the depth of the trees. Another thing you have to tune is learning rate. This is a very important one. So again, small learning rates will lead to like a more smooth decrease of the bias error. But you will need more iterations to train it. Right? So it will be more expensive. And there are 2 main approaches for solving this. So either you just set the number of estimators, the number of models as high as possible. So say that you have enough computational time for 10,000 iterations, then you set this to 10,000. And then you tune the learning rate, see how low you can get this, and then train every model for 10,000 iterations. Or you can choose learning rate that works well, and you use early stopping to avoid overfitting. The max number of features, again, like in random forest, you can choose to on the one hand speed up the computation. Like if you have a small number of max features, then finding the splits will be faster. But of course, increasing this also means more variance, so more likelihood of overfitting. And this parameter is for early stopping. It's the number of iterations without seeing any change in the validation performance. And the tolerance is how much change you would allow. Okay, so when I say that people win challenges, they don't do it with the basic version of gradient boosting, but they use something like extreme gradient boosting. This is basically a faster version of gradient boosting. It has a lot of cool tricks to speed up the training. And because it's faster, it also allows you to do more iterations. And it also allows you to work on larger data sets because it has a few tricks for allowing that. Now, first of all, they don't use normal regression trees. So normal regression trees, they're designed to work with any sort of data, right? Now, in this case, your trees only have to fit residuals, right? And that means we don't have to use, for instance, the square laws as you would normally do, but you can split the leaves so that after the split, the residuals are more similar. All right, so say that this is 0, and you have some residuals which are positive and some residuals which are negative. Then, if these are the points in your leaf, then there's some measure of dissimilarity between them, right? If you would then split the leaf like this, then after splitting, all these values are more similar, right? And so the XGBoost trees basically split the trees so that after the split, the residuals are more similar to each other, are more pure in the sense that the residuals are similar. That's one major innovation. Another one is that to speed up the finding the best splits, so say you have a feature x1 and it has so value 1. It has a number of points. Normally you would have to evaluate, well, first of all, you have to sort this data, which is O(n) log n, which is not cheap. And then you would have to evaluate every single split point. Now, what extreme gradient boosting does instead is says, well, don't bother about that. We're just going to take Q quantiles. Q is typically quite large, like 30 something quantiles. So basically it takes a number of splits according to the quantiles. And these will be defined by having more or less the same data points within each two quantiles. So we'll have the 0.5 quantile, maybe the 0.45 quantile, the 0.55 quantile. And we will only evaluate these 30-something splits, which is again a very big improvement. So Q here, the number of quantiles, is a hyperparameter. And typically this is defined as some ratio of the total number of points. Another thing that XGBoost does, specifically for large data sets, so whenever you cannot store the data in memory, you can split the data into different batches. And these can all be run on a different core or a different machine even. And for each batch, we compute a histogram of the data points. And then we bring these together into one final histogram. And then we use that to define the quantiles. Okay? Yeah, so that's the whole idea. So you can parallelize this. You can use multiple cores to compute this, which is good, right? Because otherwise, boosting is very hard to parallelize. Random forest is easy because you can just train every tree in parallel. And boosting, you have to wait for the previous model to be trained to be able to compute the residuals, right? So it's sequential. But this allows you to still parallelize it. And typically this will give you a pretty significant boost, like factor 5, 6 in speed up, which is good. Now for classifications, the quantiles are also weighted. Yeah. Yeah, gradient descent itself is sped up by not taking the first derivative, but taking the Hessian, or the second derivative of the loss function. And so it's instead of taking small steps in the right direction, you take a big step in the right direction. So each one of these is harder to compute, but it will mean that you will converge faster. It also does strong regularization by pre-pruning the trees. And when it has to compute splits, it doesn't look at all the features and all the data points, but it will randomly subsample them. So whenever you have to compute a split, you randomly consider a number of columns and you randomly consider a number of data points when computing the splits. And then there are some other tricks like supporting out-of-core computation. So it will kind of compress data in memory. It will do charting if you have multiple nodes to compute on and so on. If you want to try this in practice, XGBoost itself is not a scikit-learn, but there is the histogram gradient boosting classifier, which is sort of similar in that it also has this binning. It has these approximate quantiles, and it allows parallelization. So it's as close as you can get in scikit-learn. It is also a quite new algorithm, so maybe it will be improved over time. If you want to use XGBoost itself, you have to install the Python package. It's sklearn compatible, so it will have the fit and the score function as usual. You can install from Conda if you want to. It also has some cool tricks, like it allows you to visualize the learning curve, it has warm starting and so on. Here are some links to papers and documentation if you want to learn more. Another very popular algorithm is LightGBM. And this uses gradient-based sampling. So say that so remember that our function f is a sum of g0 plus some learning rate, so new eta, times g1 and so on. And this g1 has to look at all the residuals. All right. Now, so it has to be trained on a lot of data. And when you have a large data set, like 1 million data points, you will have 1 million residuals, and you have to train every model on 1 million points, which is expensive. So what LightGBM does is, it basically says that not all these residuals are equally interesting. If the residuals are large, they're interesting. So you would use, for instance, the 10% largest residuals. You would definitely fit on those. And for the smaller gradients, you would randomly sample a subset of them. And then you basically train your next model only in those residuals. Right? And this will, again, speed up quite significantly how fast you can train this. Yeah. It also does some smart encoding of categorical features. So if you have features which are categorical, which have multiple categories, LightGBM has some smart encoding for that. I think things like target encoding and so on, which we will discuss in the next lecture. And then there's XGBoost. XGBoost is another fast algorithm. It's specifically useful if you have categorical variables. It has different versions of target encoding. So target encoding is a way to convert a categorical feature into numeric ones in an intelligent way. It also uses something called symmetric trees. So this is somewhat counterintuitive. So what this does, it basically uses the same split for all the nodes in a certain level, right? And because it has to compute only one split for all the nodes, it's much faster than having to find the optimal split for every single node. And it turns out to also work well. And it also allows some things like monotonicity constraints. So say that you know that a model must be a non-decreasing function of another feature, Like if one feature goes up, the prediction should also go up. You could add that as a constraint into your model training. And then there's also lots of other tuning, like you can train on GPUs to parallelize things and so on. Something that we haven't discussed yet is stacking. So contrary to bagging, random forest, and boosting, we can also build heterogeneous ensembles. So these are ensembles where every model can be something different. So model 1 can be a support vector machine, model 2 can be decision tree, model 3 can be logistic regression, and so on, right? And then the idea is that you will first give the data to every model. Every model will make predictions. So model 1 makes predictions y at I, model 2 makes predictions y at 2, and then all these predictions are given to a stacking model. Sometimes it's called a meta model, but I find that a bit confusing. So let's just call it a stacker. The stacker here has to look at the predictions of all these models and has to learn how to combine these predictions into a final prediction. Right? So it will learn basically something like if you add model 1 plus model 2, or maybe model 1 is very good overall, but still give a small weight to model n and so on. So the stacker has to learn how to combine these predictions into a final prediction. You could also do this on a multi-level way. So say that you have not one stacker, but you also have another stacker, which is trained on some other models. And this also gives you predictions. So again, this is trained by other models, and maybe you have another one here. Again, trained with other models, and also gives you an output. Then you bring these three together into a new prediction of predictions, and then this is then given to a higher level stacker. Right. So you can imagine this gets super complicated, right? Because say that this one is trained on n models, and you do this m times, you'll have m times n models to train, plus the number of stackers. So this quickly becomes a very complex, complicated, slow model, right? Because if you have to predict, every data point has to go through all these models, has to be predicted. Some of these may be slow in predicting. So yeah, it's one way to get a very good model. So whenever people just don't care about speed, they just want the best possible prediction, you can use this kind of stacked or multi-level stacks. It's definitely possible. Another thing you can do is cascade stacking. Right, so this stacker here has to learn how to combine these predictions, but maybe it depends on the inputs, like the specific input values, how to predict these base learners. So what you do here is you add the inputs again to your data. So the stacker here will get all your inputs x, and then on top of that, all the predictions of the base learners, and then has to learn on that. So this has a benefit that it could learn actual relationships, like if feature x2 is larger than 5, then maybe look mostly at this prediction and so on. So you can actually learn more complex relationships that way. Very important again, the models need to be sufficiently different. If they're all the same, then yeah, it doesn't help so much ensembling them. They must be expert at different parts of the data. And yeah, like I said, it's very accurate, but also can be quite slow. Now there do exist some ways around that. So say that you have a super complex model, you can do something called model distillation to learn a simpler model out of that. But that's pretty advanced stuff. We'll discuss it later. Finally, there are some other ensemble techniques that we haven't discussed yet. So first, one thing you can do is, if you have a model which has a hyperparameter, you can build an ensemble out of different models for different hyperparameters. Right? So say you have a supervector machine, you can build an ensemble which has an SVM with gamma 0.1 and another SVM with gamma equal to 0.0001, another where SVM where gamma is 1000, right? And then build an ensemble, for instance, a backed ensemble out of all of these. And this is called a hyper ensemble. It's an ensemble of hyperparameters. This is, yeah, it sounds a bit weird, but it definitely works sometimes. What you can also do is ensemble of deep learning models. This already came up, right? Especially you can do something like bagging over deep learning models, because deep learning models are typically quite unstable. They have high variance, so on some of them makes sense. You could actually also stack deep learning models if you want to. You can do things like stacked autoencoders and so on. That's for a later date. Then there is also the Bayes optimal classifier. This is mostly a theoretical aspect, a theoretical concept. It's basically the ensemble of all possible models. So the ensemble of all possible decision trees, or one simple case could be like naive Bayes, the ensemble of all possible naive Bayes models. You could do that. It's not typically used in practice. It's mainly just theoretical. What's the best possible model you could build with some data? Another thing you can do is Bayesian model averaging. So if you have a number of models which are probabilistic, so these models will not only give you prediction, but they also give you probabilities. Right? And you can then do something like bagging. So you average over them, but so they say as a prediction P1, P2, P3, which is typically the mean, right? And has some kind of uncertainty of variance or probability, whatever. You use these together. So it's an ensemble which has a weighted average of these models, but then weighted by how probable their predictions are. You can only do this with probabilistic models. Another thing you can do is cross-validation selection. So this is basically an internal model selection. So say you have some models. So typically this is done also for tuning hyperparameters. Say you have some linear model, and you can try that with different alpha parameters. Right? And basically your ensemble, so given data X, just evaluates all of these using cross-validation, and then, so 1, 2, 3. And then from that outputs model 2, 1 as the best one to make predictions. And you can also use any combination of these techniques. Okay, that's basically it. So we discussed quite a bit. So we've seen classification and regression trees, where the representation is a tree. Loss functions either entropy or Gini for classification or square loss for regression. We use this Hunt's algorithm, which is basically an iterative hierarchical greedy search. And you can regularize the trees by the tree depth, for instance, or other ways like the maximum leaf size and so on. We've seen random forests, which is an ensemble of randomized trees. Loss function here depends again on what you want for the trees. You can typically choose that. And there's no real optimization, but you use bagging to reduce the error. Then you have AdaBoost, which builds an ensemble of stumps, uses exponential loss, and does greedy search to build this additive model. We have gradient boosting regression classification. Here we have an ensemble of regression trees. We use square or log loss, depending on regression or classification, and we use gradient descent basically to optimize the ensemble. And then we have things like XGBoost, LightGBM, CatBoost, which are basically an ensemble of XGBoost trees. They use square or log loss depending on classification or regression, and they use second order gradients for optimization. And finally, stacking, which is an ensemble of heterogeneous models, and there's a second order model that then predicts based on the predictions of the base models. Optimization and loss function depends on what your stacker is, so it can be anything. Okay, so to conclude, we've seen that ensemble of voting classifiers, first of all, can improve performance. The problem with voting classifiers is that we don't really know which models to choose, but we can use a bias variance trade-off to make some informed decisions. This leads, first of all, to bagging, in which we purely want to reduce the variance. So we do that by building many high variance overfitting models on bootstraps of the data. Again, the more different the models are, the better. So it's good to have randomized trees or extremely randomized trees, or do anything else that makes the models more unstable, more high variance. And we do soft voting over all the predictions to reduce the variance. Again, the more models, the better, but of course there's diminishing returns, and if you over smooth, you will increase bias error at the end. So there's diminishing returns. These are very easy to parallelize, and they don't require much tuning. Maybe you want to tune the maximum number of features considered in each split, but that's basically it. Boosting is the opposite. It's a bias reduction technique where we use an ensemble of low variance, high bias models, and each has to correct each other's mistakes. We can do that either by reweighting misclassified samples, and this leads to AdaBoost, or we can have every model predict exactly the residual error of the ensemble, and that leads to gradient boosting. Again, these are additive models, and predictions are the sum of all the base model predictions. You can really drive the error down to zero, but if you do too much, you will risk overfitting. This does not parallelize easily because it's sequential. It's also slow to train, but it is faster to predict, which is very good in practice. And there exist algorithms like XGBoost and so on, which are also faster to train, and they allow you to train larger ensembles on larger data sets. And finally, stacking it's a general technique that you can use to combine any number of models and have a stacker on top that learns how to combine them. So your mileage varies here, so it depends on which are your base learners. Be sure that all your base learners are significantly different from each other, but otherwise, it's a lot of trial and error typically to develop a good stacking model. That's it. Thank you for the attention, and we'll see you next week.